Recording started.
Okay, so I'll have you know that this is like my third or fourth attempt at recording this, both in Blackboard as a recording for those of you who will not be able to open my video. Always, I prefer you do the video because it's going to give you that interactive portion of the lesson that I can't provide you when I'm out. It's such amazing technology that I can create a video and do it exactly like I would do it in class, and you participate right along with me, even though I'm not there. But of course, we have had some troubles getting these things to work lately. So trying to do double duty here. And the last time I recorded, I was about 15 minutes in when I realized the microphone wasn't on in Blackboard. So it's about 9:30 on Wednesday night when I'm preparing this, and my patience is getting slim. So let's just jump right in and I guess try to eliminate some of the fluff. If I were to meet you today to study lesson 3.02, I would be asking you as your introductory activity when you first walk in the room, what's your favorite periodical? And so you might be thinking to yourself, what's a periodical? I have to think back to like 8th grade library science where we learned about reference texts like encyclopedias and dictionaries and thesaurus versus periodicals versus books and all of these things. Periodicals can be magazines. That's what I have pictured there. So periodicals can be magazines. They can be newspapers. They can be journals. If you are in a science field or really any professional field, a lot of PhDs will publish their research, whether they are literature professors or math professors or science professors. They're going to publish their findings psychology in a journal that comes out periodically. Really anything that is published with some frequency. So this word periodical takes us to the English language that we know of as the term periodically. Something happens periodically. We refer to it happening regularly or often or sometimes or with regularity, like with appointment or something like that. If you visit the dentist periodically, it's possible you go twice a year, maybe you go 3 times a year, maybe you go once a year. That's okay too. It means periodically. The periodic table has been designed to have a periodic repetition of trends, and we have talked about that now when we discussed the periodic law and the fact that Mendeleev designed this periodic table with all these intricacies that he knew about at the time, amazingly. He organized it by atomic mass and actually predicted the existence of elements no one else knew were there yet. They hadn't discovered because of the way he had organized it. But then, in addition to his 8 groups and 12 periods, he was able to notice that every 8 elements, so every time he finished a period, when that period started over, the first element of the next period had properties that were similar to the one above it. So sodium, wait, let's count now. Lithium, 1, 2, 3, 4, 5, 6, 7, 8. Every 8th element behaved similar to the 8 for the 1 8 before it. So lithium and sodium had similar physical properties. They were both shiny. They were both soft. And potassium does as well. And he noticed that trend way back when. Even in the new periodic table, the one updated to be organized by atomic number, we still do see that trend. So those same 3 elements are in the same group together. They each start off a new period. Between lithium and sodium, we can easily see there are 8 atoms between them by virtue of the fact that lithium is atomic number 3, sodium is atomic number 11, and then potassium is atomic number 19. After potassium, we actually have 18 elements in between, and it gets a little hairy, but we'll focus our efforts on the beginning half here. That repetition, as we have discussed, is referred to as the periodic law. The periodic law, in terms of the periodic table, can be difficult to wrap our heads around. This idea of periods and groups interacting, but they don't really, one creates the other. We kind of liken it to a calendar, right? We organize our time, even if we're just talking about watching TV in a week. There are different shows on different days, you know, unless you're like The Voice or American Idol, where now you own 2 or 3 days of the week. There may be certain things you do on certain days each week. Maybe Sunday you do some type of worship. Maybe Monday is your Empire night, and Thursday is your How to Get Away with Murder night, and Wednesday's your Muppets night. Whatever you do, Saturday's college football. If we're just confining that discussion to TV, we might have the same routine every week. And so every day in the week will be different. The programming on TV is different every day of the week. But when we start over again on Sunday, we see pretty much the same programming. At this time of year, you have Sunday night football, and in the mornings you have church on TV a lot. And then, of course, our regular programming, if something's not in its way, as is common at this time of year. We have the same thing going on the periodic table. All of the neighboring atoms are different from one another. Sodium does not have the same properties as magnesium. However, so that's like having a Monday and Tuesday on a calendar or in a week. When we start over that week, so we go into the next week, potassium is the first day of the week. It's Monday. And sodium is the first day of its week. That's Monday. So sodium and potassium are going to be similar because there's that repeating effect after so many days. And that's what we get when we talk about the periodic law. Now, having reviewed all that, that's where we are to this point. Today, we use lesson 3.02, which is simply called the periodic table, which is like, isn't that the whole unit? It is, but we show you some more tips and tricks here in the periodic table that are pretty straightforward and really quick shortcuts for getting information that you need. So still in this lesson, focusing on relating the position of an element on the periodic table to specifically today, we finally get to this electron configuration portion and ultimately the reactivity. And near the end of the lesson, you'll see in our mastery map here, we're going to talk about different regions of the periodic table. What do they mean? What are all these different groups called? And how do we categorize them? So here we go. If we were in our live session today, participating, I would ask for some volunteers to review our electron configurations because I know you guys are A-okay at doing these. Hydrogen, simple, lithium, sodium, potassium. Again, we're looking at the first 4 elements of group 1, so of the vertical top to bottom group. If we write them, I'm just going to ask you to take a moment, and if you're watching the Zaption video, enter what you notice to be true in the box provided. What is similar between these 4 electron configurations? And if you're watching the Blackboard recording, you can think about it too. Okay, hopefully what's staring at you like a sore thumb is that the valence electrons, and in some cases in hydrogen the only electron, is in an s orbital. Okay, so for hydrogen, the outermost electron, what we would call the valence electron, is in the 1s orbital. In lithium, that outermost electron, the valence electron, is in the 2s orbital. For sodium, the outermost electron is in the 3s orbital. And for potassium, the outermost electron is in the 4s orbital. This is not a coincidence. In fact, we'll find later on in the unit, and I will just give you a clue about it now, that the period number can indicate to us where the valence electrons are going to be. So you'll notice for hydrogen happens to be in period 1, and its valence electron is in the 1s orbital. For lithium, its period number is 2, and its valence electron is in the 2s orbital. Are you catching on to that there? For sodium, the valence electron, the outermost only electron, is in the 3s orbital. It's in period 3. And finally, I think you're getting this, potassium is in period 4, it starts off period 4, and its valence electron is in the 4s orbital. So a couple similarities you can pick out there. The biggest one I wanted you to see is that the valence electron all lies in the s. And then, of course, there's that trend with which s orbital is it, 1, 2, 3, or 4. And so we can glean that information from the periodic table. If I also ask you to look then not at the group 1 but the group 2 elements, beryllium, magnesium, and calcium, remember we did only go up to 20 protons and electrons when doing our electron configurations, so I didn't go any further than that. Take a look here and enter again what you find to be similar among these 3 electron configurations. And again, you should have sort of picked out that the valence electrons, the outermost electrons, lie in the s orbitals in each case. 2 in the s orbitals, 2 in the s orbital, 2 in the s orbital. And again, we can identify which s orbital by the period number that the element is located in. So beryllium is in period 2, so it's in the 2s orbital. Magnesium's in period 3, so it's in the 3s orbital, and calcium's in period 4, so it's in the 4s orbital. This really, the nitty-gritty of this, comes in another lesson down the road after our quiz. But I'm introducing it to you now because this idea of outermost electrons, valence electrons, does come from the periodic table. And what we end up seeing is that we can actually group the whole periodic table into what we refer to as blocks. So we would call this area over here the S block. Any element in this S block has valence electrons in the S orbital, as indicated by this pink shading here. So we did look, and just to really quickly review, our group 1 elements ended up in the S orbital and had only 1 electron in them. And our group 2 elements ended up in the S orbital and had 2 electrons in them. So again, that is not coincidence either, as our group numbers are 1 and 2 here. So if I just point this out, this superscript number kind of comes from these up here, okay? So our group 1 elements have 1 electron, and I'm sort of diverging from my major point here, but I think this will help you pick up on it later a little bit, okay? Valence electrons for these elements in the s orbital. In the blue shaded, we have all of these elements have valence electrons located in the p orbitals. And in the middle, these are our transition elements, these transition metals. They are located, those valence electrons, in the d orbital. Remembering that valence electrons, by definition, are the outermost, highest energy orbitals. They contain the highest energy electrons. Okay, this is significant because of electron configuration eventually leads to reactivity. Okay, it also suggests to us that the group number can determine the total number of valence electrons that we have. So if we can know exactly how many are in are exactly what orbital they're in, we can also know how many there are. And so what we eventually get to here, oops, I have this, what we eventually get to is that the group number is equal to the number of valence electrons in an atom. And so we'll come back to that in a second. First, I want you to just use this really quickly. And instead of green check, red X, if you are doing the Zaption video, I want you to do A and B, true and false, okay? The valence electrons of all halogen atoms, and we haven't discussed what a halogen atom is yet, they are all in group 17 or group 7. It says they reside in a d orbital. Is that true or false? And this question really just depends on you interpreting this graph. Okay, that is absolutely false. Halogen atoms end up over here on the right-hand side of the periodic table. They're shaded in blue. That means those valence electrons will end up in a p orbital. The only ones that end up in a d orbital are these guys in the center. And they're very, very unique. Okay? So going back to this idea of group number and valence electrons, this is in part why it's important that we number the groups according to those A and B designations I've been referring to over the last few days. Because as it turns out, an atom can't have more than 8 valence electrons. And we haven't talked about that yet, but we will someday soon. And if we look at the group number, it tells us exactly how many we have. So if we randomly pick sodium, we can look at the group number and say we are going to have only 1 valence electron in an atom of sodium. And if we look at carbon, well, it's in group 4A, so it's going to have 4 valence electrons. And let's again randomly pick selenium. Selenium is in group 6A. It will have 6 valence electrons. And again, remembering throughout this discussion, we totally ignore transition metals in the middle because they really don't follow a trend. They don't follow rules. Every single one of them has an exception, and they're just like way too confusing. I think even as an introductory chemistry course in college, you're not going to talk about those. I think you have to actually be a chem major and go into the next level of classes to be introduced to the why about that. Okay, so we want to practice this here a little bit. Lots of multiple choice for you. If you're watching the Zaption video, please do participate. How many valence electrons does bromine have? Bromine is atomic number 35. Does it have 4, 7, 2, or 17 valence electrons, or you really don't know how to determine this? And I have taken my numbering away there, so that'll require your contribution. Okay, correct answer here is 7. Again, if we were to number these left to right, we would get 1A, 2A, oops, 3A, 4A, 5A, 6A, I'm running out of room, 7A, and that's where bromine is, and then 8A. Okay, so I know those are kind of like off a little bit. Sorry. It's in group 7A, so it has 7 valence electrons. We need to get really used to doing this because after this lesson, you're just going to have to be expected to know that's what we're referring to. So let's look at arsenic. Arsenic is atomic number 33. How many valence electrons does it have? All right, and I'm just going to zip through here. I'm going to leave out the A's. I'm going to number 1, 2, 3, 4, 5, 6, 7, and 8. So it ends up in group 5, which means it has 5 valence electrons. How about potassium? Potassium is atomic number 19. Because potassium is in group 1, and we don't need to number any further, it will only have 1 valence electron. And I think this is our last straight up example, sulfur. Sulfur is atomic number 16. How many valence electrons will it have? Okay, again, numbering left to right, skipping the middle, we have 1, 2, 3, 4, whoops, 3, 4, 5, 6, 7, and 8. So it's in group 6, so it will have 6 valence electrons. Okay. Now, a different way of asking these same questions is to say which element would have the same number of valence electrons as sulfur. So we just looked at sulfur in group 6. And our other options for valence electrons are, for the same number of valence electrons of boron, argon, oxygen, or nitrogen. Or, of course, you don't know how to determine this. Okay, well, what we're finding here is what's characteristic to each group. Basically, what defines a group is its group number. and its group number tells us number of valence electrons. So if we're looking for how many valence electrons each of these has, we can easily identify that. Boron will have 3 valence electrons. Nitrogen will have 5 because it's in group 5. Argon will have 8 because it's in group 8. And oxygen will have 6, and it happens to be in the same group as sulfur. So that would be our answer here. So really, all you need to look at is what element is in the same group as another one. But also you could go through and identify each of them. That's good practice too. Okay, trying again if you maybe didn't get it so much on that last example. Here we're asking the same question. Which element would have the same number of valence electrons as magnesium? Okay, so we're going to take a look at our options. Are beryllium and argon. Potassium, which is not P. It's not P, that's K. K. Big K. Or nitrogen. Okay, which element would have the same number of valence electrons as magnesium? And let's go through these. Potassium is in group 1. Oh, I guess we should number them 1, 2. Okay, hopefully you're getting really good at this. 3, 4, 5, 6, 7, and 8. It'll become like second nature, I promise. Potassium will have only 1 valence electron because it's in group 1. Oh, and right away we hit magnesium and beryllium both in group 2. So magnesium and beryllium are both going to have 2 valence electrons. And beryllium is the correct answer here. However, you can also determine the total number of valence electrons in nitrogen is 5 because it's in group 5. And also argon, I believe we just did in the last example, argon would be 8 because it's in group 8. Good. I hope you're making progress. I can't see your progress, but I do trust that you are making progress. Okay, so the whole group number valence electron thing is kind of huge. It's definitely the most important piece we're going to review today. But we can also identify the periodic table is both organized and notated in a way that reveals the physical state of atoms. And by physical state, we are directing your attention down here, solid, liquid, gas, or we don't really know, it's not found in nature. And we identify these in the periodic table. Typically, all periodic tables are conformed to this format where all of the symbols written in black are solids. And that's a huge majority of the periodic table. So I'm just going to notate it here for you. Grabbing all of those or most of those solids, you can see it encompasses probably 2/3 of the periodic table or more, maybe 3/4. And we have a few down here too, solids, right? They're in black. Now, if we're looking at liquids, we're looking at the blue types. And it turns out we only have 2 elements in the entire periodic table that are liquids that is at room temperature. So if we were to find them naturally occurring, they would be liquids and not solids, and that is bromine, and that is mercury. And also those that are gases are usually in red. So I guess I should color coded my pen here. But our gases are found over here on the right-hand side of the periodic table. There's only a very few of them. I guess it looks like 6, 7, 8, 9, 10 of them. And that is to say that we breathe nitrogen and oxygen, and chlorine we know is a gas for the most part. Helium we know we fill up balloons with, that's a gas. So we've encountered some of these before. They are the only gases. And then everything printed in green is not found in nature. Well, how on earth does it exist? Scientists have actually produced them or made them. And I don't know what the formula is for creating atoms, but they have done them. They have some kind of crazy names. Like I think this name, AM, is Americanium or Americanum or something about America. This is Californium, CF. So they get a little crazy. Okay, so practicing this, knowing how to interpret the periodic table, very important. Which of the following elements is a gas at room temperature? We're looking at beryllium, labeled in black, argon labeled in red, potassium labeled in black, nickel labeled in black. Or you don't know how to determine this. Okay, best answer here is the only one shown in red. Argon is a gas at room temperature because its symbol is shown in red on the periodic table. Okay, so that's what we're looking at. We're looking at the legend here, and I'm sure most periodic tables we have a legend, but this should be something that we kind of commit to memory. Which of the following is a liquid at room temperature? So we have, again, beryllium and argon. This time we have bromine mixed in there and nickel. Or you're not quite sure how to determine which one would be a liquid. Best answer here is going to be the one printed in blue, and that of course is bromine. So this one's all about reading the legend. Beryllium's a solid, nickel's a solid, argon's a gas. Bromine's a liquid. And you have lots and lots of them to choose from for this example. Which one of these elements is a solid at room temperature? And again, we're looking at beryllium and argon and bromine and oxygen. And the best answer here is going to be beryllium, because for solids we're looking for the black printed elements. So here we have beryllium solid, oxygen gas, argon gas, bromine liquid. Alrighty, so we have reviewed electron configuration similarities in groups, valence electrons according to group numbers, and also physical state and how they're organized in the periodic table. Now we're going to look at type, elements organized by type. You'll notice this is a very, very color-coded periodic table. Kind of looks like the rainbow, right? We have red, orange, and yellow, then green followed by blue. Indigo and violet, that's a rainbow song for you. Woohoo! Purposeful. Not always provided to you in this fashion. Like usually the periodic table I give to you is just white with atomic numbers listed, because over time you will get to be used to what's what and how it goes. But each of these groups, each of the most important groups, has a name or a designation or a type that we can group together. The very first one I'm going to talk about is this group in the middle I tell you to keep avoiding, and that's called transition metals. These are called the transition metals. Transition metals, these guys right here, they're the metals we're most familiar with. When we think of metal, we think of shiny, we think of hard, we think of used in our forks and our knives and our saws and our hammers and anything, our jewelry, right? We have here silver and gold and platinum and nickel and copper and zinc and iron. I'm not sure what else. Mercury actually ends up in this category even though it's a liquid. So transition metals are those classic metal-like metal-like substances that we think of. They don't really conform to anything we're going to talk about with the periodic table. They're sort of outliers and they do different things. Okay, group one elements. These are referred to as the alkali. How about alkali metals? We wouldn't think of these as metals. Sodium comes from sodium chloride, or actually sodium is used to make sodium chloride, which is table salt. And it doesn't look like a metal, right? Of course, it has already reacted. Sodium, in its natural form, looks more like a metal. It looks silvery, but it's not hard. It actually is soft like butter. So that's interesting. Generally, because all of their physical properties are similar within a group, lithium, sodium, potassium, they're all going to be similar, and they have this alkali metal designation or name to them. Group 2 are similar. They're called alkali earth metals. And part of the reason for that is because we can primarily extract them from the earth. If you were to ever do a water analysis on your tap water, on your distilled water, any kind of spring water, not distilled water, but spring water, you'd find magnesium and calcium in it because those are natural deposits that come from rocks in our Earth's crust and Earth's core. Okay, shifting our focus to the right-hand side of the periodic table, some other special and important groups are groups 7A and 8A. 7A are called the halogens, fluorine, chlorine, bromine, and iodine. Group 8 are referred to as the noble gases. And group 8 is called noble gases. The word noble kind of makes you think of like royalty, nobility. You're really super important. They have a very, very specifically special trait that we will talk about in time as we start to break down each of these groups and what they mean and what they represent. For now, you just need to know of them as the noble gases. And am I missing anything? Maybe. We do also have groups in general. So you'll see this purple sort of staircase-like area on the periodic table. They are called metalloids. They're not quite like metals, and they're not quite like nonmetals. So this whole half of the periodic table, all of them, whether they're alkali metals, alkali earth metals, or transition metals, they're all metals. On the whole left-hand side, that's 2/3 of the periodic table. On the right-hand side of this staircase, over here, we have nonmetals. And we will talk about all these and exactly what they mean in time, not today. Nonmetals. And then, of course, this staircase area here are called metalloids. They try to be like metals. They try to be like nonmetals. They're somewhere in between. So that's sort of elements organized by region or by type. And as I said, we will get into more detail with what all of those are and what they mean. But should be able to, at this point, function with the periodic table and generally know those very important groups, alkali and alkali earth metals, as well as halogens and noble gases. So true, false on this one. Think about it, answer it if you're watching Zaption. All alkali earth metals have the same number of valence electrons. Alkali earth metals, I'll give you the hint, group number 1. Would they all have the same number of valence electrons, true or false? Answer is true. What we have learned today in the beginning of class is that the group number equals the number of valence electrons. Oh, not money. Not money, number of valence electrons. And so all alkali metals are in group 1. That means they all have 1 valence electron. And that the fact that they all have the same number of valence electrons lends to their chemical properties and their reactivity. If they all have basically the same number of valence electrons, they're going to behave similarly in chemical reactions and things like that. Okay. It says elements in period 2. Now remembering period 2, what's period? Think about it. Elements in period 2 share the same physical properties, true, false? Answer now. Okay, answer is false. Period 2 goes across, left to right, horizontal row. We said this is like a week on a calendar. Monday is different from Tuesday, is different from Wednesday, Thursday, Friday, and Saturday. They are all different. You have different schedules, different TV programming. But when you start over again on Monday, then you have the same thing as you did last Monday. So across the period, not the same properties at all, very, very different. Up and down a group, yes, that would be true. Okay, and that summarizes everything I had for you for this lesson. Hopefully you found that enriching. Hopefully you found it a little bit more practice-oriented than maybe if you looked through the course lesson yourself. I am not going to revisit any of these topics in our live session unless I find that both of my attempts to get this information to you via Blackboard recording and video failed. Otherwise, you will have to reference this by recording at some point. I will expect by Sunday, even though it's Friday when you're watching this, that you will have attempted as many times as you needed to the 3.02 homework. There was only one. We're spending one day on this, one homework for it. Next week, we start a lab right away. So there's quite a few assignments you want to get done before the weekend. One was your Unit 2 test. That's huge, 100 points. You don't want to zero there. Get it done. Another one, homeworks, 2 homeworks for 3.01 and 1 homework for 3.02. So it's a heavy work week in chemistry. Make sure to get all that work done as soon as possible. I, of course, am out, which is why you're seeing me virtually in a video. I will be checking my K-mail throughout the weekend. Get me if you need me. I'm going to be working on your test grades and all sorts of stuff. I work all weekend long. Maybe not every hour of every day, but certainly every day. So I'll do what I can to respond to any messages you leave me. Good luck and enjoy the weekend. Thanks for your attention.
Recording stopped.